Most people are aware of the fact that light carries energy. We walk under the sun and our skin absorbs the photons and we feel the warmth. But few people are aware of the fact that light also carries momentum. That's perhaps because we are too large. If we were the size of a dust particle, then we would be pushed around by the momentum of photons, and we would know that light has both linear momentum and angular momentum. So the simplest way to find out the momentum of light in vacuum is through this thought experiment due to Einstein. It's called the Einstein box thought experiment. Suppose you have a box that is empty. The inside of the box is vacuum. It's sitting on a frictionless rail, and it has a length L, mass M, and there is a blob of material on the left-hand side. At some instant of time, a pulse of light emerges from the left wall with energy E, which is equal to mc squared, m being the mass of the photon in flight. And Einstein assumes that there is some momentum P, and the purpose of this thought experiment is to determine the value of that momentum. We don't know it at this point. So this pulse propagates to the other end, gets absorbed on the right-hand side. And in the process, when the pulse first leaves, the backlash momentum minus P is given to the box, and at the end, when the pulse gets absorbed, the momentum goes back into the box, and the box stops. So the time of flight is the length of the box divided by the speed of light in vacuum. The recoil velocity is minus p divided by the mass of the box, and therefore the box displacement is given by the product of the two. Now Einstein said there is no external force acting on the system, so the center of mass cannot be displaced. The center of mass displacement then is given by the mass of the photon times its displacement, plus the mass of the box times its displacement. Setting them equal to 0, canceling m's and l's, you find out that the momentum is given by energy divided by c. Okay. Okay. So the okay. Sure. So the momentum is given by the energy divided by c, speed of light in vacuum. And if it's a single photon, its energy is h bar omega divided by c. That would be the well-known momentum of light in vacuum. Now let me show you some simple applications of this property of light. Suppose you have a piece of glass. This is ordinary glass, refractive index n, cut in the form of a prism. Suppose a pulse of light arrives at Brewster's angle of incidence. So this angle theta b is the Brewster's angle. The light is linearly polarized as shown, and therefore the reflectivity is 0. So the light bends according to Snell's law, goes inside the prism. If the apex angle is chosen properly, then the incidence on the other facet is also at Brewster's angle, so all the light comes out. There is no reflection anywhere. 100% of the pulse goes in and then comes out. And you notice that in the process, the vertical momentum of the light hasn't changed, but the horizontal component has changed. It went from left to right before entering the prism, and it goes from right to left when it exits the prism. And this change of momentum is equal to a force, and that force F is shown here. The force F is exerted by the passage of light through the prism, on the prism itself, and the prism is going to be pushed forward. So if you like, this is a light-activated bullet. Now, there are two different ways to calculate the force. One is using the momentum of light in vacuum, exactly as I mentioned. And the second method is to use the force of electric field and magnetic field on the dipoles inside the prism. And if we do everything right, we should get exactly the same answer. The two methods should agree. So the force equation is tied to the momentum of light. Light also has angular momentum. So if we take a pulse of light that is circularly polarized, has energy E, its angular momentum will be energy divided by the frequency omega. When this pulse goes through a half-wave plate, this is a transparent half-wave plate, Let's say it's anti-reflection coated, so everything goes through, no reflection. When the light emerges, it will have the opposite sense of circular polarization. That means the angular momentum has changed, and the result of this is that the half-wave plate must start spinning. So in practice, if you take a half-wave plate, which is only 10 or 20 microns in size, and use 10 or 15 milliwatts of laser power, you will see that the half-wave plate starts spinning at a few hundred rounds per minute. And that's the basis of some of the micro machines that are being developed today. This type of angular momentum, by the way, is known as the spin angular momentum of light due to the polarization. In addition, we have orbital angular momentum, which is described here. Suppose you take a piece of glass, ordinary glass, transparent, cut it in the form of a cylinder, as shown here. The bottom is flat. The top is in the form of a spiral ramp. So if your plane wave comes through, and this plane wave is linearly polarized, the light that comes out has its rays bent as shown, because each segment of the cylinder acts like a prism, and it bends the rays as shown here. So there is a component of momentum in the xy plane, and that component goes around the z-axis, and so we have angular momentum in the emergent light. So incident beam is linearly polarized. It's a plane wave. The beam that comes out is an optical vortex, and it has angular momentum. And depending on the height of this discontinuity, which could be a 2 pi phase shift or 4 pi or any integer multiple of 2 pi, you can get nh bar of angular momentum per photon, n being the number of 2 pi discontinuities. So again, this angular momentum will be transferred to the cylinder. The cylinder will start rotating in the opposite direction. What if the incident light is circularly polarized? So now when the light emerges from the cylinder, we have both spin and orbital angular momentum. And the way we can distinguish between the two is by placing a small absorptive particle in the path of the light. Because of the orbital angular momentum, this particle starts rotating around the z-axis. And because of the spin angular momentum of the light, the particle starts spinning on its own axis. So if you change the sense of circular polarization, you'll see that the particle goes in the opposite direction on its own axis, but it continues to go the same way around the z-axis. There are many other applications of the momentum of light, the mechanical properties of light. And here's a recent application group from Professor Kippenberg in Switzerland. And what you see here is an electron micrograph of a ring resonator. Everything is made of silicon dioxide, ordinary glass. The color is fake. So there's a base that has been narrowed, so there is very little thermal contact between the ring and the base. The ring resonator is shown here. It has a diameter of 30 microns. When light is coupled into this ring, radiation pressure makes it expand, and that property is used to cool down one of the modes of mechanical vibration. The radial breathing mode can be cooled down, and this system, in fact, has been cooled down to very close to the ground state of the quantum mechanical vibrations. So here you see the light that is coupled into the ring shown schematically. So what I have said so far is about the momentum of light in vacuum. There is no controversy here. Everyone knows the h bar omega divided by c is the momentum of light in vacuum. But what happens when light is inside a material medium? In a material medium, there has been a debate for the last 100 years as to what the momentum of the photon is. According to Minkowski's theory, the photon momentum in vacuum must be multiplied by the refractive index n. According to Abraham's theory, the photon momentum must be divided by the refractive index n. And so there has been a controversy for the past 100 years. Many theoretical papers have been published, some supporting Abraham, some supporting Minkowski. Experiments have been done, some supporting either one. And so the controversy remains to date. I really shouldn't be talking about photon momentum here because everything I say is classical. We're talking about classical theory of electrodynamics. So we really should be talking about the density of momentum of the electromagnetic field. In Minkowski's theory, it is given by D cross B. In Abraham's theory, it's given by E cross H over C squared. So when I talk about photons, all I'm taking is a pulse of light, divide its energy by h bar omega, and call it the number of photons in the pulse. So I want to argue here that the momentum of light inside a material medium is exactly halfway between the Abraham and Minkowski values. It's neither this nor that. It's exactly halfway in between. And here's the simple argument. Suppose I have a piece of glass of refractive index 1.5. Any refractive index will do. But just for the sake of argument, let's say that we have a piece of glass. A pulse of light comes in with 100 photons. It gets reflected. The reflectivity of this glass is 4%. So 4 photons come back. 96 go through. So now in vacuum, out here, we know exactly what the photon momentum is, h bar omega over c. Conservation of momentum tells us that these 96 photons should carry the momentum of 104 photons in vacuum. Therefore, each of the 96 photons should have a momentum equal to 104 divided by 96 h bar omega over c. And if you write it down, reflection coefficient of the glass, you will find that this is exactly halfway between the Abraham and Minkowski values. So that's the total momentum inside the piece of glass, halfway between Abraham and Minkowski values. Now, of course, we have to recognize that inside the medium, there are two kinds of momenta. There is electromagnetic momentum and mechanical momentum. So the argument that I just gave you pertains to the total momentum, which is the sum of these two types. The total momentum is halfway between Abraham and Minkowski values. Now, how much electromagnetic momentum do we have here? Let me first mention what I mean by mechanical momentum. Let's say that we have a piece of glass of refractive index n, which is given by the square root of the dielectric constant, and a pulse of light is propagating inside this medium of certain widths, electric field, magnetic field shown. If you calculate the force that the leading edge of the pulse exerts on the material medium, you will find this formula with a plus sign. Dielectric constant, permittivity of vacuum, magnitude of the electric field here. And if you calculate the force exerted by the trailing edge, you will find the opposite, the same force with a minus sign. So the leading edge accelerates the atoms as it goes over them. The atoms will acquire a momentum while the pulse lasts, and then the trailing edge pulls the atoms back and stops them. So as the pulse propagates, the atoms of the material medium have acquired the momentum, just between the leading edge and the trailing edge. And that's what we call the mechanical momentum. And in addition to that, we have electromagnetic momentum. So I'm going to now show that the electromagnetic part is given by the Abraham formula. The total momentum is halfway between Abraham and Minkowski, and therefore the difference between the two is the mechanical momentum, which is associated with the motion of the atoms of glass. So here's the thought experiment of Balazs, dating back to 1953. It's a simple thought experiment. And from this thought experiment, we learned that the electromagnetic part of the momentum inside the medium is given by the Abraham formula. What we have here is a piece of glass sitting on a frictionless rail. It has dielectric permittivity or magnetic permeability or both. And we look at two situations. The first situation, the piece of glass is stationary. A pulse of light propagates in vacuum for a certain length of time. So the mass of the pulse moves from this point to that point, but the piece of glass remains stationary. In the second experiment, we let the pulse go through the glass, anti-reflection coating here. We don't have to worry about reflections at either surface. Now, because the pulse slows down inside the glass, the group velocity is less than c, the pulse emerges somewhat behind the previous case. And so this distance which is related to the group velocity inside the medium, is important in this thought experiment. And what Balazs said was that this system is not subjected to any external forces, therefore the center of mass of the system should be in the same place in the two cases. And when you follow this argument with very simple calculations, you will find that the momentum of the photons inside the glass must be given by the vacuum value divided by the refractive index. And the refractive index must be the group refractive index, not the phase refractive index. So this argument tells us that the photon momentum is given by the Abraham momentum, but that's only the electromagnetic part. The total value is what I said earlier. It's halfway between Abraham and Minkowski. So now that we have discussed the momentum of the photon, let's talk about the force. Because as I said earlier, the force equation should also give results that are in perfect agreement with the arguments we obtain from the momentum concept. So here's a table from Feynman's lectures on physics. He summarizes the entire classical physics in this table. And what he has are Maxwell's equations here, the Lorentz law of force, and then Newton's law in its relativistic form, and then the law of Newtonian gravitation. So basically, for electrodynamics, we have Maxwell's equations plus the Lorentz law of force. Now, last May, I published a paper which got me into a lot of trouble, caused some controversy. And in that paper, I said there is some trouble with the Lorentz law of force. It's incompatible with the special relativity and momentum conservation. So on a charged particle, the force is given by the Lorentz formula. If you have a continuum, you have to look at the charge density times the electric field, the current density, that's QV, crossed into the magnetic field, and that gives you the total force density. These are Maxwell's equations, and I like to use the macroscopic equations because I believe these are fundamental, they are exact, they tell us most of the things we need to know about the electric dipoles and magnetic dipoles. So D and B are defined here. And so in electromagnetic theory, according to the macroscopic equations, we have four sources: free charge, free current, polarization, and magnetization. And these sources give rise to the electromagnetic fields, E and H. I tell my students that these equations are the Rodney Dangerfield of classical physics because they don't get enough respect. These are exact equations. There's no need for smaller scale time averaging. And of course, they're reducible to microscopic equations. But as they are, they contain a lot of information about what electric dipoles and magnetic dipoles are. So without doing any physics, we can just do algebra, define the bound charge density, bound current density according to these formulas, put them in Maxwell's equations, and we see that D and H disappear. So now everything becomes charge and current according to the classical theory. And so we have a total current, which is the sum of free and bound currents, and we have a total charge, which is the sum of free and bound charges. And relativity applies, so we can transform. If we go from one coordinate system to another, from inertial frame to another, we can find position coordinates, time coordinate, dipoles transform relativistically, and fields transform relativistically. So again, I repeat, the total force density is given by the Lorentz formula, and there is a corresponding torque density that is given down here. So here's the example that I showed in my paper of last May. Suppose you have a point charge and a point magnetic dipole sitting at some fixed distance in the x prime, y prime, z prime frame. There is no force, there is no torque between the two, so everything is stationary. Nothing moves, no dynamics here. But suppose you look at the same system from a moving frame, from the xyz frame, which has a velocity v relative to the stationary frame. Then you use the Maxwell's equations, you use the Lorentz transformations, and you use the Lorentz law, and you find that there is a torque acting on the magnetic dipole, and the magnitude of the torque is given here. This is the exact relativistic result. And so in the stationary frame, there is no torque on the dipole. In the moving frame, there is a torque, and that shows that there is some problem with the Lorentz law of force. You can't have torque in one frame, but in the other frame. Now, it turns out that there is a formula that Einstein published in 1908. It's known as the Einstein-Lob formula, and that formula is given here for the force density. For free charge and free current, it's the same as the Lorentz law, but for electric dipoles and magnetic dipoles, it's somewhat different. And Einstein treats electric dipoles and magnetic dipoles symmetrically in this formulation. That's the whole basis that he uses for this formula. And the corresponding torque formula is given here. So if you use the Einstein-Lob formula, then you find that there is no torque in the moving frame. So everything is fine. So I suggested that instead of using the Lorentz law, we should be using the Einstein-Lob formula to calculate the force and torque in general on electric dipoles and magnetic dipoles, as well as free charge and current. So let me summarize my conclusions here by saying that I believe it's the macroscopic equations that are exact and self-consistent, and in some respect, they are superior to the microscopic equations of Maxwell. The Lorentz law is incompatible with special relativity and conservation laws unless we take the hidden momentum into account. But without the hidden momentum, it's the Einstein-Lob formula that gives us consistent results. The correct force law, I believe, is the Einstein and Lob's. The energy, everything we need to know about energy is given by the Poynting vector. The electromagnetic momentum density is given by the Abraham formula. And the angular momentum is also given by the Abraham formula, both for spin and orbital angular momentum. And these postulates are complete, consistent with the special relativity, consistent with the conservation laws of momentum, energy, and angular momentum. Thank you very much for your attention.
There is a case where I think there is absolutely no ambiguity, and I would like to know, because I am not sure at the end if which of the two formula is a good one. So there is a case where I have no doubt on the result, and I would like to know how the two models apply. If you have an evanescent wave,
yes,
the k vector parallel to the surface is well known. It's n h bar k times the sine of the angle, etc. This can be measured without any ambiguity by dropping atoms on it and seeing the recoil of the atom. And we are sure that it is n h bar k parallel, okay? So which of the formula agree with that?
Yeah, well, that's the Minkowski momentum. When you reflect a photon from an object, an atom or a mirror, submerged in something else, like a mirror underwater, then the momentum that is transferred to the mirror is the one that you just mentioned, n times h bar k. But some of the momentum is also transferred to the liquid or the surrounding medium in the opposite direction. When you subtract the two, you get that formula that I gave you earlier, halfway between the two. So in vacuum, when you shine light on a mirror, the momentum goes to the mirror. But when the mirror is submerged in something else, some of the momentum is transferred to the host. And that has to be taken into account.
So my question refers to the earlier part of your talk before you started into the media, which I think should be non-controversial.
Yes.
So I hope these are easy answers. Well, one is really historical. The Einstein's box experiment, or thought experiment, was one that I remember as being an alternative demonstration of E equals mc squared, the momentum already being well known from Maxwell. And I was just wondering historically whether there were also uses in the other way and whether it was by Einstein. But that's just a historical question. But the real question is this. You talked about the orbital angular momentum of light, and you said that, well, you can do this something by a spiral phase plate. There's any number of other ways you can make orbital angular momentum, and you end up with something that's that gives a momentum of n h bar per photon.
Yes.
Now, that's, to my way of thinking, certainly going to be true if the spatial mode of the light is pure. What I'm wondering is, if I've got spatially incoherent light, will this still apply, or can I have non-integral angular momentum if I've got spatially incoherent light, so that I don't have to apply a continuous phase condition on the light?
Yes. The first part of your question, historically, Maxwell already knew that electromagnetic fields have momentum. Maxwell died in 1879. That's the year that Einstein was born. So Maxwell gets the precedence. But Maxwell's argument was based on the fact that the electric field excites the electrons on the surface of a metallic mirror, and then the magnetic field pushes them back.
Sure.
Somewhat different from Einstein's argument. Yeah, the second part of your question.
Well, what I was wondering was, historically, though, Einstein first, at least the way I read the historical record, used this not as a demonstration of radiation pressure, but as a demonstration of E equals mc squared, assuming the Maxwell result. And I was wondering whether, historically, he also used it the other way. Okay. Because in 1907 is the first that I'm aware of this thing, and he'd already done the E equals mc squared in 1905, yeah. And then he said, well, here's another way you could get it.
Right. Yeah, well, I don't know the answer to that question. What I just told you was the story that I learned from Feynman's lectures. And that's what Feynman says.
Okay.
Okay. Then the second part of your question, you can have situations where the orbital angular momentum is not an integer multiple of h bar. The simplest example I can think of, not necessarily with incoherent light, but suppose you get a biaxially birefringent crystal and shine a beam of light at it. Hamilton's conical internal refraction tells you that the light that emerges will be in the form of a ring. If the incident light is circularly polarized, the light that comes out is linearly polarized around the ring. As you move around the ring, you see that the linear polarization changes, but it changes only by pi. So you come back to the same location and the polarization has flipped. And that can't be, because that's a discontinuity. But what happens at the same time, the phase of the light also changes by pi. So by the time you come back to the same point, the polarization is not flipped. That light that comes out of the crystal has an angular momentum of 1/2 h bar.
So this is sort of like a half vortex in a...
Exactly.
Yeah, okay.
The same problem in a different context, I think, was recently addressed. And this is the question of the momentum of a matter wave as it goes into a region of refractive index, namely a gas for which there are interactions.
Yes.
And the question is, what is the momentum of the particles while they're in the gas and when they come out? And I know Dave Pritchard wrote about this within the last couple of years. I can't cite the article, but I think it's the identical problem in a different context.
Yes, the paper I remember is the one by Pritchard and Ketterle and their students. And they talk about a photon inside the BEC. Yeah. And the value that they find is the Minkowski momentum, which is exactly the value that Alan mentioned. And my response was that the difference between that momentum and the value that I mentioned goes to the BEC itself. Mm-hmm. But the one that you mentioned about the atoms having a momentum inside the light field, that I'm not familiar with. But this is similar to the question of the momentum of phonons. The pseudo-momentum is believed to be n h bar k.
Thank you, Professor Masud.
Thank you.